When we look across the harbor, we can't see the buildings clearly with the naked eyes because they are so far away.
In the folktale 10 Brothers, one of the brothers is called Tally-Eyes, who can see things far away.
A tale is only a tale, but this story still reflects man's wish to broaden his view of the world.
But the human eye is limited. If we wish to look farther or see more closely, we need the help of optical instruments. Can be said to be the first optical instrument. They were invented some 700 years ago.
About 300 years later, Galileo made a telescope from spectacle glasses and used it to observe the celestial bodies.
He's discovered that the moon was not smooth. There were black spots on the sun and satellites around Jupiter.
These were all major discoveries in astronomy.
The birth of a telescope spurred the development of astronomy. The microscope was then invented. This opened the door to microbiology and allowed men to see what the human eye could not see before.
With the help of microscopes, biologists discovered cells and microorganisms, and biology entered a new stage.
All optical instruments, including the telescope and the microscope, are made up of different lenses. Lenses are usually polished and made from pieces of glass. Both surfaces of each of these pieces of glass are curved. A lens thick in the middle and thin on the edge is a convex lens, whereas one that is thin in the middle and thick around the edge is a concave lens.
In fact, many transparent objects, such as a glass of water, a light bulb, or a drop of water, can bend light rays like a lens.
This glass filled with water, for example, is a water lens. The water in the glass has a curved surface, just like a convex lens, which is thick in the middle and thin on the sides.
Let's try to see things through the glass. Put this piece of cardboard paper close to the side of the glass. The words on the paper are magnified by the glass. So a glass of water, like a magnifying glass, can magnify things.
An arrow is printed on a piece of cardboard paper. Put a glass of water in front of the paper, close to the arrow. When viewed through the glass, the arrow is magnified, and the direction of the arrow is the same as that of the arrow on the paper.
Now move the glass slowly away from the paper. We notice that as the distance between the glass and the paper increases, the arrow becomes blurred. When it becomes sharp again, the arrow becomes reversed, but it's still magnified.
If we continue to move the glass of water away, the arrow will still be inverted, but it becomes smaller and smaller.
This is because of the refraction of light by the water in the glass.
The images formed are sometimes magnified
And sometimes reduced.
Sometimes real.
And sometimes virtual.
These are the properties of an image formed by a convex lens.
A beam of parallel light emerges from a ray box and passes through a cylindrical convex lens. After passing through a convex lens, the parallel light beam is converged. As a convex lens can convert a parallel beam into a converging beam, it's also called a converging lens.
On the other hand, a beam of parallel light diverges after passing through a cylindrical concave lens. So a concave lens is also called a diverging lens.
This is a magnifying glass. A magnifying glass is in fact a convex lens. Put a convex lens on a newspaper and you can see that the words are magnified. So a convex lens can be used as a magnifying glass.
Face the magnifying glass towards the sun. Move your hand under the glass. You can feel heat on your hand at the bright spot.
Put a piece of paper in this position and we can see a spot of light. As a convex lens is a converging lens, it converges the parallel light beam to a point. If we put a match here, it will soon burst into flame.
A microscope can help us see things which we can't see with our naked eyes.
There are several types of microscopes.
To understand how a microscope works, we can use a drop of water.
And a magnifying glass
To make a microscope.
A magnifying glass is in fact a convex lens. When we use a magnifying glass, the object to be observed must be very close to the lens. Then we can see an upright and magnified image.
A common magnifying glass can enlarge an object 2 or 3 times. Some magnifying glasses can enlarge 20 to 30 times. The larger the curvature of the lens, the higher the magnification power.
A transparent water drop is like a lens with a large curvature. Place a banknote on the table. Put 2 pencils on it. And use the pencils to support a transparent plastic sheet. Then place a water drop on the plastic sheet. This is a magnifying glass.
Through the water drop, we can see that very small words on the banknote are magnified. This shows that a water drop is a lens with a high magnification power.
The rounder the diameter of the water drop, the larger the curvature. Put 2 water drops of different sizes on the plastic sheet and look through them. You will notice that the objects are much larger when viewed through the smaller drop.
Although a water drop with a large curvature can magnify an object to a greater extent, the image is distorted. The area viewed through the drop is also very small. Only the middle part of the observed object can be seen clearly. The sides are all blurred.
With only a magnifying glass, we can't achieve the effect of a microscope.
But if we use 2 magnifying glasses and place them at a particular distance from each other, objects will be magnified twice and look much bigger.
There are 2 basic components in a microscope. One is a convex lens placed close to the object to be observed. This is called the objective. The other is a convex lens close to the observer. This is called the eyepiece. First, the objective forms an inverted, enlarged real image. The image is then further enlarged by the eyepiece, which acts like a magnifying glass.
We can use a water drop as an objective and a magnifying glass as an eyepiece. First of all, print some small letters on a piece of paper and use these as the object to be observed. Through the water drop, we can see an enlarged and inverted letter. This is an enlarged real image. Then use a magnifying glass to observe the water drop. At first it seems that we can't see anything, but don't worry. Carefully adjust the distance between the magnifying glass and the water drop, and then you'll see a letter that's clear and much enlarged.
Monocle optical microscopes are, of course, more sophisticated than our water drop microscope.
But the working principle is the same as that of a water drop microscope.
There seems to be nothing special about this fish tank, but if we look upwards from the side of the tank, we can see that the surface of water is silver in color. It looks very much like a mirror, reflecting the objects underwater. We can't see any of the things that are above the water level.
This phenomenon is related to the total internal reflection of light. When light goes from glass or water into the air, total internal reflection may occur.
A light ray is emitted from a ray box. When it hits the curved surface of a semicircular glass block, it goes into the glass. After reaching the inner surface of the glass, the incident ray is divided into two rays. One is reflected into the glass, and the other is refracted into the air.
If we slowly increase the angle of incidence on the inner surface of the glass, the light ray refracted into the air becomes weaker, and the reflected light becomes stronger. A point is eventually reached where the entire incident ray is reflected into the glass and no refraction occurs. The surface of the glass is just like a mirror. This is known as total internal reflection.
A beam enters a right-angled prism. Total internal reflection of the light beam will occur on the inner surface of the prism. The reflected beam emerges from another side of the prism. On the inner surface of the prism, only reflection occurs. No refracted light emerges from the glass. The prism has turned the light beam 90 degrees.
The beam can also enter from the base of the prism. Total inner reflection occurs twice in the prism, so the light beam is turned around 180 degrees.
Look inside a 90-degree prism, and we can see that its inner surface is like a mirror reflecting the incoming light. But it is better than a mirror in that when it reflects light, little light is lost. So when we make a periscope, we can use it in place of a plain mirror.
Total internal reflection has various applications. For example, on the road surface there are reflectors on the road dividing lines. At night time, the reflectors reflect the light from car headlights into the eyes of the driver. This helps the driver to see the dividing lines better. By means of total internal reflection, the plastic prism installed in the reflector reflects the incoming light rays.
Here's a glass bottle. A torch is placed behind it. Water flows from the bottle. Place a finger in the outflowing water. Watch carefully. The finger is illuminated by the torch. So long as the finger follows the column of water, it is illuminated. Light seems to be traveling along the curved path of the water. But doesn't light travel in a straight line? It's strange.
On the face of it, light seems to be travelling along a curved path. In fact, light has travelled in straight lines. Because total internal reflection of light rays occurs many times on the inner surface of the curved path of the water, in the end, the light comes out from the other end of the path, so it appears to us that light is following a curved path.
Light travels along a piece of glass fiber in a manner similar to the way it travels in a column of water.
Light enters from one end of a piece of glass fiber. Total internal reflection occurs repeatedly on the inner surface of the glass fiber. So light can travel from one end of the glass fiber to the other, and will not leak into the air through the side of the fiber.
The principle of total internal reflection is also applied to this display. These transparent strips are made of glass fiber.
Light enters from one end of the glass fiber and comes out from the other end after several total reflections. A lot of light spots are formed as a result.
With the advancement of science and technology, these glass fibers can be made as thin as a spider's thread.
Glass fibers that are used to transmit light are called optical fibers.
On the medical front, optical fibre has been used to make endoscopes for inspection of the stomach, the esophagus, the duodenum, or even the heart. In the 80s, video endoscopes were developed. The doctor can use the video endoscope to direct high-intensity laser beams to treat wounds and remove small tumours in the body.
Optical fibers transmit information much more efficiently than copper wires.
A pair of metal wires can only transmit 1,000 odd telephone messages at a time.
But theoretically, a very thin optical fiber can transmit 10 billion messages at a time.
And the flashing signals made by a laser can be transmitted through optical fiber at a high speed.
In addition to telephone communication, optical fibers can be used to transmit signals for automatic telemachines, EPS service, fax, teleconferences, internet, and interactive TV.
So optical fiber is very widely used in everyday life.
In the morning, when the sun appears to have risen above the horizon, in reality, it is still below the horizon.
In the evening, when we see the sun approaching the horizon, it is actually already below the horizon. This phenomenon is a result of the refraction of sunlight by the atmosphere around the Earth.
The sun is approximately 150 million kilometers away from the Earth. The Earth is surrounded by a thick atmospheric layer. When sunlight enters the atmosphere from outer space, refraction occurs. The refractive effect in the atmosphere can bend the incoming beams of the sun by an angle of 35 minutes. So when we see the sun going down the horizon, it has, in fact, already gone below the horizon.